Okay, so week 6, you're learning about polynomial functions. And this is where students really struggle because it gets really into algebra and you end up doing a lot of factoring. You have a lot of theorems to understand, a lot of definitions to understand. And one of the things that I see people have trouble with frequently is end behavior. And if you have to go on to pre-calc and then go on to calculus, this idea of end behavior is actually really important. So, so I've prepped a thing here. So basically definitions of what a polynomial is. Now, back in week 2, when we were talking about factoring, you were introduced to an idea of a polynomial. We're revisiting it again, but now in terms of graphing it, rather than just looking at, factoring it. So a polynomial function is defined in such a way. So I've got this very mathy looking equation here. Basically, you just have a series of terms added together, and you have a variable with exponents on it. And we always arrange it from the highest exponent down to the lowest exponent. So we've spent some time on quadratic functions where it's x squared and then an x and then a constant. So a polynomial in general can be something higher than a quadratic. A quadratic is a polynomial. A linear equation is technically a polynomial, but we can have higher exponents like exponent 3, 5, you can go as high as you want. The general rules are that your exponents are all whole numbers, so we don't have any fractions or decimals in the exponents. And all of our coefficients, those are the numbers in front of the x's, are real numbers, which means we don't have any imaginary numbers in our equation. We could end up with imaginary numbers when we factor it, but in the equation itself, there's no imaginary numbers. And so when you look at something in this form, the first term, or basically the highest term here, that is called the leading term. It's called the leading because it comes first. And so the number in front of that is called the leading coefficient. And then that highest exponent that we see is called the degree. So that's the degree of the polynomial. And so this is some definitions that are going to pop up in your assignment and on the quiz and stuff about like what is the leading term, what is the leading coefficient, and what the highest exponent is. And these are actually really important because understanding this terminology and then recognizing the numbers actually allows you to know what the polynomial will look like, the general shape of the polynomial, without actually even graphing it. So these numbers will tell you what it looks like, and you don't even have to put in a graphing calculator, which I think is kind of cool, that you can figure it out just by looking at these numbers. So with polynomials, we have 2 basic shapes, and everything goes down to these 2 basic shapes at some point. So we've seen a quadratic, which we called a parabola, and that is on the left here. It has an even degree, which means that it's degree 2. That's the highest exponent on a quadratic, and 2 is an even number. Basically, any polynomial that has the highest degree as an even number is going to look something like on the left. So that would be if it has an x to the 4th as the highest, or an x to the 6th, or x to the 8th. Anything that has an even exponent as that highest exponent is looking like on the left. Then the opposite is if it has an odd exponent, it looks like the shape on the right. So what we see on the right is actually an x cubed here. I'm just going to move my keyboard slightly. So what we see here is x cubed. And if you have something higher, like an x squared, or not x squared, x to the 5th or to the 7th, they all have that same general shape. So basically, if you can look at that degree based off of whether it's even or odd, tells you which of these it's going to look like. And if you're wondering about, well, what happens if I just have a regular x where the exponent is 1, a linear equation still kind of has this shape. It just doesn't have that curve in the middle. And basically, the higher the degree, the more curves you have sort of in the middle. So long term, they'll look like that shape, but in the middle, there might be some extra humps. And it's the same thing here with like an even. There may be some extra humps in the middle, but if you zoom out enough, it's going to look like one of these two basic shapes. So that's why it's important to understand degree and recognize what the number is, because it tells you which shape it falls under. And so if you're taking, like, say, a multiple choice quiz and you have a series of graphs, or you're supposed to pick which graph matches the equation, this, just knowing the degree can help you narrow it down because you know the basic shape. Now, the next thing after the degree is that leading coefficient, the number in front of it. And that basically tells you if it's going up or it's going down. So if it's the leading coefficient is negative here, oops. So if it's negative, it goes down. And so you can think of it, well, negative, like a frown, you know, negative people, something negative happened, you're sad, frown. You know, that's one way you can remember this. And it opens up if we have a positive leading coefficient. And that leading coefficient, again, is just that highest term. So the leading coefficient is that number in front. So if it's a positive number, it opens up, and if it's a negative, it opens down. Yes, Julie.
So where you were just talking about how, like, on the graphs, like, if it's like cubed, it's going to be like almost like a sideways S. So
yes.
With that, like, if it's okay, like if it's to the 5th power, does that mean that there's gonna, okay, like, I know you said that there'll be other humps, but will there be like a hump for each power? Is that how that works?
Yeah. So basically, you take the power and you subtract 1, and that basically kind of gives you how many humps you have, or how many curves, if you want to think about it that way. So like a quadratic has 1 curve, so 2 minus 1. A cube, it doesn't look like it, but it kind of has two curves there. They're just kind of flattened, you know. So yeah, so now it doesn't always follow that, but that is the general rule. You know, there's the other things added on do affect that, but that's the general rule. And that's the maximum number of humps it will have. Okay. So that's actually a really good question. So like x to the 5th, I'd have 1, 2, 3, 4 humps in order to have it go back up in the general shape.
Okay.
And this is also kind of leads us back to the leading coefficient test. So what you want to pay attention here on the leading coefficient is what's happening to the rightmost part. So when it's positive, that leading coefficient is positive, the rightmost part of it is going up. So like here. But when it's negative, the rightmost part goes down. So if we have a negative coefficient of like x cubed, it's like flipped upside down. So that right part is now going down instead of up. And then you would still, if you had x to the 5th, you would still have like 4 humps in there. But
it would just be going down because it's negative, right?
Exactly. So it's like telling you where is the right going, and then the left part of it depends on if it's even or odd. If it's even, it goes in the same direction as the right. If it's odd, it goes in the opposite direction.
Got it. Thank you.
So this brings us exactly to end behavior. So end behavior is just what happens at those edges, the left and right points, and we ignore what happens in the middle. So in the middle, we may have more than one hump. We may have 2 humps, we may have 5 humps, whatever humps you have. That sounds really bad now that I'm saying that out loud. I guess we could, I don't know what other else to call it, but you've got this squiggly going on in the middle. So that can change, but it's the endpoints, the left and the right side, that we're concerned with end behavior, because those are the ends of the polynomial. And so when you're asked about end behavior, it's just basically what is happening to y as your x is going either to negative infinity, which is on the left, getting smaller and smaller, or to positive infinity on the right. So as x goes, to the extremes in either direction, what is happening to y? Is y going up towards infinity, or is it going down towards negative infinity? It's going to be in one of those directions. It's just a matter of which direction. So the tricky part is the notation for it, which I have right here. So we indicate x getting really, really big or getting towards larger values of x as x, and then the arrow, and then this is our infinity symbol. And so that's basically read as x goes to infinity. So it's getting bigger. And then if it's going in the opposite direction, we use negative infinity there. But the arrow doesn't change direction. The arrow is just read from left to right, and we just indicate, is x getting big or is x getting small? Then for our y values, we don't use y, we use f of x because it's a function. But it's the same symbolism. It's just, is it going towards infinity, which means we're going up, or is it going towards negative infinity, which means we're going down? So we use this notation that looks kind of hard to read, and what makes it even trickier is that sometimes they write it in words. And so then you have to kind of translate, what does this mean in words? So like for the y values, if we're saying that that y is getting large, we would say y increases, so it's getting bigger from left to right. Because we're moving, we always read everything from left to right. So if we move from left to right on the graph and it's getting bigger, you would say it increases from left to right. And then, of course, if it's small, you would say it decreases. And this that I've written right here would be for the right side. In the left side, if we were to write the left side of the graph, whether it's going up or down, and we're putting it words, then you would just switch it and say as you go from right to left. So you're kind of thinking about, you're always starting in the center, and then you're either going from left to right or right to left to kind of determine where is y going. And I think this will make much more sense when we start seeing like pictures and things like that. So here's even. So even, they're going in the same direction. And if that leading coefficient's positive, they both go up, or if it's negative, it both goes down. And so you can see that we've got dashed lines here, and that just indicates we don't care what's going on in the middle. We're only caring about those end pieces. And so you can kind of see how it's described in words here, whether we're going up on the left or up on the right, or down on the left and then down on the right. So we can use those words, but we also have the symbols here. So you can see on the left here, so it says as x goes to negative infinity. So that means as x goes to negative infinity here, y is going to positive infinity. It's going up. That's what that is translated as. And then on the right side, as x goes to positive, or I think x goes to positive infinity, y is also going to positive infinity. It's just they're on two different axes. If it helps you when you're trying to do this, like on the number line, I'll put in positive and negative infinity. You can do the same thing vertically if it helps you remember which direction you're heading. So the bigger numbers, the more positive goes towards positive infinity, the negative goes to negative infinity. The best thing that I would do is be able to draw the picture or know what the picture looks like, and then go to this slide, like when I send this out tomorrow, you can print out the slide or copy it down or whatever you do, and just read it off of the slide how to write it, because trying to remember how to write it properly it's difficult, and I find that less important than actually understanding what it looks like. Because it's really the understanding of what it looks like that matters more than did you write it exactly as asked. So when you're doing your homework or taking your quiz, use this as a guide so that you can write it properly, and you can put the symbols in the right direction, because they're going to ask you, is it positive infinity or negative infinity? Is it x? Is it f of x? Is it going up? Is it going down? Focus more on understanding the shape, and then just use this as a guide, because that's going to aid you further on. The notation, unless you're going to be a mathematician, that's less important. Or if you're going on a calculus, you will have to understand some of the notation here. But in general, it's just, you just want to know, well, what is it doing long term? Because that's what this is asking about. Is long term, am I increasing? Am I making money if you're in a business or something like that, or am I losing money? Is it going down? Like that's what we're looking at here. Are there any questions? Okay. So for odd, again, just understand whether it's going to go up or go down, and then use this as a guide. So if your leading coefficient is positive, what's kind of nice is that when your x goes positive, so does your y, and when your x goes negative, so does the y, so they kind of match. But when that leading coefficient is negative, that's where it does a flip-flop, and so it's kind of easy to get confused there. So if you want to write in your negatives or your infinity symbols on your graph, you can, to kind of help, remind yourself, okay, where are we going? So I've got 4 examples here, and I'm also going to bring up Desmos after we do these to graph them, so that way you can connect what we're doing with the equation to what it actually looks like. So I'm going to just start with g of x here. So we've got negative 1/2 x to the 6th plus 8x to the 4th minus x cubed plus 9. So the highest exponent there is 6. 6 is an even number, so we know immediately that this is going to be even. We have an even degree. So our choices are, it's either going to look like a U, or it's going to be upside down, an upside down U. And I leave a gap in the middle because with that end behavior, we don't really care what's going on in the middle. So I leave a gap there to indicate that it doesn't matter what the middle is. We're just looking at the left and the right parts. Now, next is we look at that coefficient. So the coefficient is negative. So our leading coefficient is negative, which means that right side is going negative. So that means our whole thing is going down. So we have 2 choices of the shape, and we have to pick the one where the right is going down. And if we want to kind of put this in the words and the symbols, we would say, you can say on the left side first, x is going towards negative infinity. So the left side always has x going to negative infinity. Our y value, our f of x, is also it's going down, so that also goes to negative infinity. And then the right side is always your x going to positive infinity. And then our f of x is going down, so that's going to negative infinity. So, and you can read that directly off of those graphs that I had on the previous slides. That's how you can identify the end behavior there, basically. You know, for me, the most important thing is being able to graph it and pick which picture it belongs to. But you're also going to be tested on writing it, so just use that guide. So let's move to the right for k of x, because those bottom ones are a little trickier, so we don't want to do those just yet. So k of x equals 11x to the 7th minus 4x squared plus 9x plus 3. So that highest exponent is 7, and so that makes this an odd degree because 7 is an odd number. So we have two choices because they go in opposite directions. We have the one on the left where that right side is going up, or the one on the right where the right side's going down. So we've got those two choices. Now our leading coefficient here is a positive 11. So the leading coefficient is positive. So I'm going to just abbreviate coefficient. So if it's positive, that means the right side is going up. So that means it's going to look like the first one that we have here, where that right side is going up. And so we've just identified the end behavior. And we would say as x goes to negative infinity, we can also fill in the other one, positive infinity. So the left side is going down, so f of x goes to negative infinity. The right side is going up, so f of x is going to positive infinity. And if I forget to say negative or positive, I'm sorry. When you're talking about things with infinity, it's really easy. I think that I'm saying them in the right places, but I would not be surprised if I accidentally forget. Earlier today, I was asking my partner if he needed a fork or a spoon, and instead I said, do you need a spork or a food? So if I say the opposite or mix things up, let me know. So I'm going to bring Desmos over here so we can graph these two before I get into the more complicated ones. Oh, why does this keep doing this? Oh, there we go. Okay. The past two live sessions I've had, Chrome has frozen on me as I've been trying to show it, so I was afraid it was going to do that, but it didn't, thankfully. Okay. So I'm going to graph the first one. So that was g of x equals negative 1/2 x to the 6th. And you can see as soon as I put in that x to the 6th, it has like that, the parabola shape, and it's going down, it's going negative like that negative coefficient has. Oops. But we also have other things here that affects the shape. So plus 8x to the 4th. And so you can see, oh, when those other things get added on, that's what creates those humps, is the other terms added on. Those affect what those look like. Okay, so now I'm going to have to really zoom out here so you can see it. I'm going to, let's see, negative 10, 10, whoops. Okay, and the y value, that, let's see, let's try 100. Going really, really tall here. Oh, wait, almost got it. There we go. Okay, so I just had to modify my scale, but this is what it looks like. And so the end behavior long term, the left side's going down, the right side's going down, and that matches what we found when we're looking at that leading term. But you can see that there are kind of humps in the middle. So x to the 6th has at most 5 humps. We've got 1, 2, 3. So we're not guaranteed to have 5, but we can have a maximum of 5. So we may have fewer of those. And in this case, we have 3. So that's what this polynomial looks like. I think polynomials are so cool because you can get some really interesting shapes out of them. So I just really enjoy them. So I'll turn that one off, and then let's graph k of x, which is 11x to the 7th. Oops. 7. So you can see that before I type in the rest of it, we have our end behavior here. So they're going in opposite directions. The left is going negative, right's going positive, as we determined. And then as I enter in the rest of the terms, and now this one I got to change. So in this case, the exponent is 7. We'd have at most 6 humps, but we actually really don't have, we have maybe 2 here. You can see that this kind of looks maybe like there's a hump here. And sometimes they interpret this as how many turns do you have? How many times does it kind of change direction? And so in this case, it looks like it doesn't really change direction except for like 1 point. But we would have a maximum of 6 times that it could change direction. If I go back to the g of x and we look at it that way, let me zoom out again. We can say, okay, it goes up, down, up, down. So you can also think of it as it changed direction 3 times, but there's like 4 different pieces of it because there's 4 sections between the up and the down. So that's another way that you can kind of think about the going up and down sort of thing. So now let's tackle the bottom ones, because these are different because they're not multiplied out. And so that is, you can still figure it out even if it's not multiplied out. It just involves a little more thinking. And that's the tougher part. So if you're doing end behavior for something like these where they're already factored, sometimes it's easier to multiply it out, but multiplying these things out would take a long time by hand. Like the one on the left, we've got lots of things multiplied. So I'm going to show you how to do it otherwise. As far as it goes, like if you're given something like this where they're factored and you're on a quiz or a test, I would recommend you type it into Desmos and then using that as your guide. But I'm going to show you how to do it by hand. So first off, we need to figure out the degree. And so we have these things that are factored. If it doesn't have an exponent, you can put an exponent on it. So I just kind of wrote ones for on the n of x because there's 2 factors that don't have exponents on the parentheses. And then we've got one that is 3. Our degree here is you add all those exponents up. So 1 plus 3 plus 1, we get 5. So this is a degree 5. Whoa, that's a weird line. So this is equivalent to if we multiplied it out, we'd end up with an x to the 5th. So from there, that's an odd degree. So again, I could put in my 2 choices. And I know it's going to be one of those 2. Now the next part is we have to kind of think of, we need to figure out that leading coefficient. And it's not as simple as just taking that -2. Because we also have a coefficient in front of the x inside one of the factors. If there was no numbers in front of any of those x's inside the parentheses, it would only be that number in front. But in this case, it's not. So when this gets multiplied out to find that leading coefficient, we're going to have that -2. And then we have that 3 on the inside. And that would basically have that 3 on that exponent along with it. And that would be essentially what the leading coefficient comes out to. So if you just ignore all of, if you ignore the x's, you ignore the numbers that are added on, this would give you an idea of what that leading coefficient would look like. So 3 to the third is 27 times -2. That gives us a -54. So that's a negative leading coefficient, which means that that right side is going to go down. That's going to be negative. So I'm not going to bother writing this stuff in blue. I want to graph this for you guys. So we have n of x. So let me turn this off first. I've got my -2, and then we have x plus 4, and then we have 3x minus 1 to the third, and then, oops, I gotta get out of the exponent, x plus 5. So right now, because I'm in a small graph, we can't really see what it is, so I'm going to zoom out. Okay, so now I have to kind of reset my, because just zooming out is not going to be helpful. So I need to change my x. Let's do -10 to 10 again. Okay. And then I need to get my y values higher here. Let's try 3,000. That's not enough. Let's try 4,000, 5,000. There we go. Okay. So this is what it looks like when it's graphed. And so it's got these really deep changes here, and then it has like a little thing here. But the end behavior, those outside parts, are exactly what we figured out. So the left side is going up, the right side is going down. Because it ends up, it's an odd degree, so they're going in opposite directions. And that coefficient will end up becoming negative, because of that little trick that I did, where I basically just took the 3 to the third here and multiplied it by the -2 and just kind of ignored everything else. Now, if you want to actually figure out what this multiplies to, there's another website that we can use to do that, because it will take a long time by hand. But it's called Wolfram Alpha. So it's just wolframalpha.com. It's a really neat website. But you can type in our function here. And so now let me type it in again. -2, x plus 4, 3x minus 1. To get to the exponent, use the little caret button above the 6, the caret symbol. Oops, third, not the 6. X plus 5. And then I can hit enter. And so it gives us it gives different plots. Now, you don't want to really pay attention to these plots. So the first one is just zoomed in a section, and it's misleading because it doesn't show you the negative part on the right where it goes down. But this one here actually does show you that end behavior essentially. But this is what it multiplies out to. So it's expanded form, and you can see that leading coefficient is that -54 that we did. So if you were to multiply it by hand, it would be this really long thing. So you can use Wolfram Alpha to kind of check your work, but you have to understand what you're looking for, because you don't want to use just, because you got two different graphs here. So you have to understand, what am I looking at? Which one's the correct end behavior? So that's why I recommend looking at a Desmos and then using that if we understand the rules about the leading coefficient and the degree, you know which one's the end behavior graph. So that kind of gives you an idea. And then you can also use it to check your work for zeros. but you would still need to know how to do that on your own, because when you take the quiz and you show your work, you're going to have to be able to work that out by hand. But you can at least check your work. And then it gives you a whole bunch of extra stuff. There's calculus stuff here. Like, this website is great. It tells you a whole bunch of things, but way more than you need to know. What we were just interested in is, what does the equation look like if we multiplied it out? And it's this big giant thing here. So are there any questions on n of x right here? Okay, so let's do the same thing for q of x. So I'm going to put in, for anything that's in parentheses that doesn't have an exponent, I'm going to add a 1. And so we need to figure out our degree. 4, 5, 6, 7, 8. That's exactly right. I hadn't even counted it yet. So we've got the 4 that's on the x to the 4th plus the 3 plus the 1. So that's our even degree. So we know it's going to look like either the smile or the frown. So now for our leading coefficient, I've got the -5. Now here in front of the x, I have a -1. And then that has an exponent of 3. And then in the next thing, I have a 2. But that exponent is 1, so I don't need to write an exponent there. So I'm just looking at what are the coefficients in front of all the x terms, and then what is the exponent associated with that. So we have, let's see, -1 cubed. Following the order of operations, exponents come first, so that would be a -1. Then I can multiply that by -5 to get 5. 5 times 2. So our coefficient here is going to end up being 10. And so that's positive. So that means the right side is positive. And so that narrows down which of the two possible shapes that we have. So I bring up Desmos again. I love polynomials because of the fact that I can kind of figure out what the shape looks like just by looking at like the numbers. I think it's really cool. I don't know if you guys think it's cool, but I think it's kind of neat. What did I? Oh, I keep hitting the minus sign instead of the equal sign. Okay. Let's make sure I didn't mess anything up here. Oh, I forgot my minus sign in front of there. I was like, that's not matching because I forgot my minus. Okay, so double checking. Okay, yeah. So you can see that end behavior matches where we've got the left side going up and the right side going up. It's even, and that coefficient would be positive, and so that's got the positive shape. And what's interesting here, so we've got our hump down here, but if I zoom in, there's a little tiny one right here that you can barely see. So that's always really interesting. And these little dots that it marks, these are the zeros. And zeros are really big when we're solving polynomial functions. They're often used if you have to go on and do calculus, and actually some business, I think they tell you the shortcuts. I know economics, they actually talk about things that are derivatives, and which is essentially calculus, but they don't call it as much. They don't really say that, but you do this like little shortcut math formula, and then you look for all the places where it's equal to 0, and those are like your special points. They tell you where the maximum and the minimums are, but you can kind of zoom in and you can see how it's got these interesting humps. So I'm going to also type this into Wolfram. I don't know if this is going to copy and paste, but I'm going to give it a shot. I don't know if it's going to interpret that.
It's going to work. Usually I have problems with that.
Oh, it did! It actually knew that. It knew exactly what we were putting in. That's really cool. So that's a nice trick that if you type it in here, if you paste it in here, it actually will do it exactly right. What you're looking at here, this messy stuff, that is a math programming language called LaTeX. It's spelled like latex, but the X is pronounced like a K because it's the Greek symbol for X, which is a K sound. So it's just translated it into the math programming language. But you can see that we've got the end behavior graph right here. And then you can see when you multiply it out, that leading coefficient is at 10, exactly what we figured out with the little shortcut thing. So you can double check all of your work here. And of course, sometimes it gives you stuff in really weird formats like this one. I don't know why you'd want it in that format. That just looks kind of weird. I think it was trying to factor it. I'm not sure. So you want to be careful about what you see, but it's a good way to kind of check your work. So that's basically everything you need to know about end behavior. And we call it end behavior because that's what happens at the ends, essentially. It's really not too bad. It's just a matter of knowing what you're looking at and then knowing what that tells you. So do you guys have any questions?